This is another introductory video discussing de Moivre's nth root theorem. This time I'm focusing on cube roots, but mostly it's going to be taking it pretty slow again. So I've gotten some of the preliminary stuff out of the way. Like, we have this complex number here. I know I'm going to be taking cube roots of that thing. So what I did was I went ahead and found for us the modulus by taking the square root of the real squared plus imaginary squared parts. And that just turned out to be 24 square root 3. You'll notice it looks a lot like this thing, and when you only have a real part or an imaginary part, it's super easy. But I just want to point out something before we move on from modulus. It is also possible to think of it this way. The square root of 64 times 9 times 3. That's the same thing as 24 square root 3. And when we're doing cube roots in a moment, it'll be helpful to keep that in our pocket. Now, the angle I haven't quite worked through yet. You see here, this is, let me change colors. You see here, this is inverse tangent of the imaginary part over the real part. Well, so far so good. We've done that plenty of times before, but what happens when the real part is 0, right? We got to divide by 0 here. That's weird. If you're doing this in your calculator, of course, your calculator is going to barf, but you need to be smarter than a calculator and remember that a tangent function on the unit circle has places where it is d and e. Remember these vertical spots at pi over 2? There's a d and e and another one at 3 pi over 2. So the question is, which one of those do we have? Which one is appropriate? Well, if you look again at our rectangular coordinates, you'll see that is going 0 horizontally, right? The real direction is 0. And it's 24 root 3. So some distance in the imaginary direction, which is straight up, positive I. That's just straight up. So right here, we've got a pi over 2 for our angle, and that's what produces the d and e's. Okay, so moving on. Now we're going to do cube roots, and for this, I want to set n equal to 3 and replace all the n's with 3. So there's an n, there's an n, there's an f. Compare this back to your original formula. All that's changed is I moved all the n's to 3's. Okay, great. Now, what we're going to do is use this working formula right here. This is our cube root formula, and substitute in the r value, the theta value, and k equals 0, 1, or 2, depending on whether I want the first, second, or third root. So let's do the first one with k equals 0. Okay, if I set k equal to 0, right, that 2 pi k is now 0. Look what I get. I get the cubed root of r. Now, that's the cube root of this thing. And you see why I kind of wanted to rewrite it this way? This is equal to, this thing right here, is equal to the square root of 64 times 27. And both 64 and 27 are perfect cubes. So it's going to make it a little bit easier to work through this cube root thing if you have a factor tree built in. Anyway, what I'm trying to say is the cubed root, here's what I'm trying to say. The cubed root of 24 radical 3, which is kind of annoying to have to deal with. Build some factor trees. You will eventually get yourself down to a simplified form, which is 2 radical 3. Okay, but I don't want to spend a lot of time going over that. So all of these are going to have 2 radical 3 up front. All of these roots. And then the only question is, what is the angle that goes inside them? Okay, what's this angle going to be right here? This angle is going to change for each of them, but the form is going to be pretty much the same. Then you'll have I sine for each of them. Okay, and one more I sine for the first one. Okay, great. So let's go find that angle. The way I'm going to do it is using this root formula again. Remember, I set k equal to 0, so what we have left is theta divided by 3. Well, what's theta? Theta is pi over 2, so this becomes pi over 6. And that's it for the first root. Now for the second root, we have to think, what's going to happen when k is not equal to 0? Okay, in particular, see what I'm adding here? I'm adding 2 pi k divided by 3. Well, what if k is 1? That becomes an addition of 2 pi over 3. Okay, so what is pi over 6 plus 2 pi over 3? Well, that's the same as 4 pi over 6. So this becomes 5 pi over 6. And there we go. That's our angle for the second root. 5 pi over 6. And now notice how in going from the first root, the 0, w0, to w1, the second root, I added 4 pi over 6. You do the exact same thing again, because this is now, this 2 pi k over 3 thing, it's now going to be 4 pi over 3 for the third root. So we add another 4 pi over 6, and we get to, I think, 9 pi over 6. And the pattern that you're seeing here, where it's plus 4 pi over 6 each time, is no accident. That is a very, very real thing. And you will see that pattern every time you're doing roots. In other words, it is the same size jump in theta every time. Once you figure out the size of the jump, this formula gets a whole lot easier, because we don't need to do the k stuff and the, all that. So a visual way of trying to describe what I'm doing here is, I keep drawing this unit circle. I don't want a unit circle. I want to draw your original z on this graph. Okay, z is, what did we have originally? It was like something that looked like this. Okay, that's 24i. And then I said, okay, great. What's the first cube root of that? And we got this thing over here. We got a smaller modulus, right? And we got a pi over 6 angle. So there was my first root. That was w0. And then my second root we found was 4 pi over 6 over. Well, that was right here. Okay, there was w1. And then the third root, now I wish I used a different color. Third root was right here at 9 pi over 6, w2. See that nice symmetry? That's always going to be playing out when you have roots. That's one of the most beautiful things about complex trigonometry on the coordinate plane.